Here we will start a new topic. It is called block diagram. In our previous lecture, we talked about the transfer function. What was the transfer function? Transfer function was mathematical representation. We discussed it. Mathematical representation of input-output relationships. Here, input and output relationships. The ratio of output and input. It was the transfer function, right? We have seen that. Now, today we will talk about the block diagram. What is a block diagram? You see, the word is diagram. That means it is a graphical representation. Graphical representation of input and output. Same thing. The difference is in the transfer function we derive it mathematically. The block diagram we will derive it graphically. Graphically, like by solving different diagrams, blocks, we will do that. So the block diagram, it is a graphical representation of the relationship of input and output. So we are talking about the graphical representation. So we need to draw some blocks. This is a block. This block is a rectangle block, not square, rectangle. So this block is a rectangle block. Which is this, for our example. Now, inside the block, there will be some information. Maybe it is a description or the name of element. So, which type of mathematical operation it will be written here. It will be shown here. Inside the block, there will be whatever the mathematical representation of our control system, it will be shown inside the block. So here we have a block. Inside the block we are repeating the mathematical operation, specific mathematical operation, and here we have the input and output will be shown with some arrows. This is the arrow. And what this actually defines, these are the arrows. It represents the direction of information, how the signal, how the system is flowing. Here, the system is flowing from X to Y in forward direction. So we are using forward arrows. If it is back, then we will use backward arrows. I will explain it later on. So this is just a simple example of the block diagram. What is the mathematical representation for this? The mathematical representation is just simple, like this, dx dt. This y equal to dx dt, we can represent it by using this block diagram. This is a block diagram representation for this y equal to dx dt. Now, how the signal is flowing from x to y, because the signal always flow from input to the output. So we must need to define first what is the input of the system, what is the output of the system here. So we can say this is the input and y is the output of the system. So we will define it, x will flow to y through a differential operator. This is a differential operator, DDD. Suppose if I will give you one more example, like y is equal to integration of x dt. Integration, another operation. So how we can define by using block diagram? First of all, you need to find out what is the input and output. So here x is the input, y is the output. So the signal will flow from x to y. The signal will flow from x to y by through a block. And what will be inside the block? That will be different mathematical operation. Mathematical operation. Which mathematical operation? Integration. Integration of dt. That's how we define the block diagram. We represent the block diagram. We will talk about more details today. Today's lecture is based on this whole block diagram. Okay, so in a block diagram representation, there are two important points we need to understand. Two important points. One we call summing point. What is summing point look like? Look at this. Summing point is a point where the information will join here. The information is going here. Look, x is going here, y is going here. We do not define it by rectangle block, we define it by a circle. Circle. So here there are two information. Look, the information is incoming to this point. This is the summing point. The information is incoming to this point. Coming to this point. And the output will be outgoing. Here both are incoming and the output will be outgoing. So the output will be x plus y, depends on which mathematical operation it is. Addition, subtraction. Suppose if it is this, is shown here, then it will be x minus y. Summing point. This is the summing point. Many information can join in one summing point. Different information can join in one point. Not the same. Different information. Different signal. Different signal. Like here, both signals are subtracting here. Minus. Here, three signals, different signals, not the same, different signals are adding here. So x plus y plus z. In some book, it is mentioned by this cross. Same thing. Some book you will see this, some book you will see this, and inside there will be this. Inside you will see there will be this positive, negative, like that. So it is the same thing. So the output is the algebraic sum of all the inputs. So a number of inputs may enter in a summing point. Number of inputs, it can be many or more than one. There is one more point we need to understand, that is called takeoff point, which shortly we call it a node. So here, this takeoff point, shortly we call it a node. What is a node? Node is a point from where the same signal will go to different branch. here node. In this point, this one we call the node. Okay. So we have one signal x. This x will go to in different branch. Here it is going to this branch, and this branch. In different direction. It can be forward direction, it can be backward direction. Here we have a node. And we have a signal. This signal is going in this direction. This signal is going to another direction. Forward direction, backward direction. Same direction. Same signal can go in different direction. That point we call it node or takeoff point. But it has to be same, one signal. So if one signal goes to different points, different directions, then we call it a node or takeoff point. So there are 2 points in the block diagram you need to understand: summing point and takeoff point. Summing point, many signals can join in that point. Takeoff point, same signal will go to different direction. Same signal will go to different direction. So these are the 2 basic things, thing you need to understand for the fundamentals of block diagram. Now we will see one example here. Here we have an x3 is equal to a1, x1, a2, x2 minus 5. How can we explain? How can we derive it? First of all, you need to define input and output. What is the input here? Anyone? What is input? How can you define input? How can you define input? If you have many signal, x1, x2, x3, x4, x5, many things, how can you define it? You will define it because in the output there will be only one. In the output side there will be only one with no constant, with no gain. Here x3 is single. That means this is our output. This is our output. And this x1 and x2 will be inputs. If you cannot define inputs and outputs, you cannot draw the block diagram. To draw a block diagram, first of all, you need to define the inputs and outputs. Now, the inputs, we have multiple inputs, 2 inputs, and 1 gain, constant value, gain, minus 5, and output. So the signal flows from input to output. So, first of all, we will write down x1. We will write down x2 because these are the inputs. We define the input in the left side, and then we will define x3 here. x3. Now here we have a1 x1 plus a2 x2 minus 5. So this x1 is multiplied with a gain a1. So we will have a block that will have a1 because it will give you some multiplication. Both will multiply and it will give you the value of a1 x1. Okay. Same thing for a2 x2. a2 x2. This will give you the value of a2 x2. Now this a1 and x2, a1 x1 and x2, a1 x1 and x2 are added. So here, what you will do? There will be one summing point. There will be one summing point. So the direction will be like this. And here we have a positive sign. So here we will have a positive sign. Here we will have a positive sign. but we have one more, -5, right? So -5, how do you write it? -5. So you can write this -5 like this. You can write it here or here. You can write it like this. Because this is just nothing again. Constant value, -5. So you just keep it like that. And so here, this pi, it will be minus, because we have a minus sign. So it will be minus. All these three are added and gives you a value of that together. The output will be x3. So the output will be x3. That is the block diagram representation for this equation. It is given here. We have, and this is the whole representation. X1, x2, and 5. 5 we have a negative sign, so it will be subtracted, and all together inside the summing point. After that, it will go 2 and x3 now. So simple function, but our control system is quite complicated, large. So our block diagram will be large, very large. We will look at that one by one. Suppose first one here, this one, how do you derive that? Let's do the first one. X2 is equal to A1 dx1 dt plus 1 by dt x1 dt. First of all, what do you need? You need to define input and output, right? So what is input here? What is input? What is the input? Anyone? X2 or X1? X1. This is the input. I have X1. I have X1. Same input. And this is output. Look, this equation can be given in another way, like this. X2 minus A1 dx1 dt is equal to 1 by b integration of x1 dt. It can be given in another way. So you must need to define the input and output precisely. So how do you define it? I told you, first of all, you need to define the output. Output is alone, no operation. Output is always alone, no constant value, no operation will be there. It only x2, x3, x4 like that. But with the input there will be mathematical operation. There will be some gains with the inputs. But with x3 there is nothing. So that's how you will define the output first. If you can define the output, then you can easily find the inputs or input. Here we have one input. So now what we need? We need to follow this. Look, we have summing point, we have takeoff point. We already have seen the summing point. Many signal, different signal is joined in the same point. Takeoff points, the same signal goes through different direction. The same signal, we have the same signal, x1. So here we have x1. This x1 will go through a node here. This is the node. Through a node, it goes to two directions because there are two separate, different mathematical operations. So one direction it will be here, another direction it will be here. Separate direction. So it will go through the separate direction, different direction. Why? Because there are two different mathematical operations. One is what? Differentiation, d dt. And another one, integration of dt. Differentiation and integration are separated, right? Different. But it is going the same signal. I am differentiating and integrating. So x1 is goes to this. So it will give you a value of dx1 dt. And here it will give you a value of x1 dt. Right? Now we have one more thing. It is constant gains are multiplied. So here we will need to multiply with the gains. Here we need to multiply with the gains. So this one will give you a dx1 dt. Here 1 by b integration of x1 dt. Now these two are having addition. So we will have a summing point here. Summing point. Summing point. This direction we must need to define the direction. We have a positive sign here, we have a positive sign here. So positive and positive. Then the output, the final output is x2. So this is the mathematical graphical representation of this equation. The next, we have one more here, x3, second one, 2x3 is equal to a1 d squared x2 dt squared plus 3 dx1 dt minus bx1. So define the inputs and output. What is output here? Output. Here. What is the output? x3, right? x3 is output. Because there is no mathematical operation, no gain, no other is here. So it is just a variable. Now we have how many inputs? 2. Here we have one input. Here we have another input. 2 input. x1 and x2. So we need to draw the block diagram. How do you draw the block diagram? So first of all, you need to write down the inputs x1, x2. Now this x1, we have multiple x1, 2x1, 2. That means we need to use a node. Here. We are using a node, and this will goes to 2 direction. Signal will goes 2 direction. So in 2 direction. Now what are the mathematical operation? First one, we have dt, differentiation. So we have a differentiation, ddt gives you dx1 dt. Now again, it is multiplied by a gain, constant gain, that is 3. So here we have another block that is 3. So first one is done. Now second one, we have a node that is goes through a signal x1, and this x1 is multiplied with a constant gain b. So here we just write down like that. We have a b. Now these two will have a summing point. Summing point. So here we have a summing point. We have the direction like this. Now here we have a positive sign. Positive sign. Here we have a negative sign. Minus. I will also have one more signal. X2. So x2 it is having d squared, dt squared. So this is a derivative. First of all, it will have a derivative d by dt. Gives you a value of dx2 dt squared. Dt, dx2 dt. But I need d squared x2. So there will be one more dd differential operator gives you a value of d squared x2 dt squared. Now here we have a constant gain a1. It is multiplied with a constant gain a1. So we have one more block, that is a1. Now this also it will be added with these two signal. So it will send to the summing point. And what is the value? This is plus. We have a plus. Here we have 3dx1 dt. Here we have bx1, 3dx1 dt, bx1. Here we have a1 d squared x2 dt squared. So all the signals are having a mathematical addition, and then all the signal will goes to the output. Now x3. Block diagram representation. This is all about the block diagram representation. Any equation, any mathematical equation, you can represent a block diagram through a block diagram representation. Why we need that? We will talk about it later on. Why we need to use this block diagram representation? We will think about it later on. But just learn how we present the block diagram out. So for the differential equation, integral equation, any other particular function, sinusoidal function, or any other functions, any mathematical functions can be derived through a block diagram. So we use the block diagram representation to find out a standard form of a control system, closed loop control system, feedback control system. Feedback and closed loop system are the same. What is that? That is automatic control system. Feedback control system, closed loop control system, actually called automatic control system. So we need to derive a standard form for that. Standard form. That is called canonical form. So this canonical form is derived by this diagram. What are these diagrams? You already know about the diagram because you have learned that here this R is defined as an input of our control system. Input, and C is defined as output of the control system, closed loop control system. And here this is what we call that G. It is called open loop transfer function. Open loop transfer function, and this is feedback This E, what is this? It is error. What is that error? We know that is called SSE, steady state error. SSE, steady state error. Okay, so here we have seen that we already know about that. We are just defining it by simple block diagram. So this is a block diagram representing graphical representation of the feedback control system. Now, what we need, what actually we need to find? We need to find out closed loop transfer function, because we need to find out the automatic control system transfer function. So closed loop transfer function, it is C by R. Sometimes you will see CS by RS. Same thing, because it is in Laplace domain, it is not in time domain. So sometimes you will see A, sometimes it is shortly it is written C by R. Same thing. So C by R, we can define it from here. G by 1 minus plus GH. G you can find it, there will be given H feedback, you will find it, and there will be given these values G 1 minus plus GH or plus minus GH, this and this. It depends on what? Depends on your this feedback value. If it is minus, then the function will be plus. If it is plus, the function will be minus. Here it is given minus plus, that's why it is written plus minus. If I write here this plus minus, then it will be minus plus. So for negative feedback, there are two types of feedback, positive or negative. For negative feedback, minus CS by RS is equal to G by 1 plus GH. Negative sign here for the negative feedback. And for positive feedback, plus feedback CS by RS is equal to G by 1 minus GH. Remember that? There will be doing it. That's why this is plus minus minus plus. And the same thing will happen for this. This is nothing but SSE, steady state error. So we need to find out the steady state error. We already told you that we must need to make our steady state error zero. Because no steady state error, how we'll have a stable control system. So how do you make this steady state error ratio? How do you find it? To find the steady state error, we need to use ES by R. ES by RS, which is equal to the same. According to that equation, it is 1 plus minus GH. Again, this sign depends on which type, positive or negative feedback. If it is positive, it will be negative. If it is negative, it will be positive. So that is the steady state error ratio. Okay, now why we need to learn this? Because any complex control system, by using block diagram reduction technique, we can reduce it in this form. Any complex system, we will see a large, big complex system. That that complex system can be reduced to this form. That's why it is called canonical form. Canonical means standard form. Any control system can be reduced into this form. So that after that we need to solve this. We can find out the closed loop control transfer function, then we can find out the steady state error, everything. But first of all, we need to solve the control system. We need to reduce the control system by block diagram reduction technique. So we must need to learn the block diagram reduction technique now. So here we have the control ratio of the closed loop transfer function G Cs by R is equal to Gs 1 plus minus Gs Hs. It is in Laplace domain. That's why we are using S. And inside, in the denominator, this equation 1 plus GH. This inside the denominator, this one involves the characteristic equation. Characteristic equation. Characteristic equation is equal to 0. That is the equation. Sometimes we need to find out the characteristic equation. So after you find out that Cs by Rs, so the denominator term we call the characteristic equation. Sometimes we need to solve that equation too. Now the different types of block diagram relationship we will talk about. The first one, the block diagram reduction technique, we need to use it because generally the control system is quite complicated. Very big large control system we have. It is not that like this. This is very small system. It is nothing. Very small system. But in our large control system, there will be, it is much more complicated. So we need to use a block diagram reduction technique, systematic block diagram reduction technique, so that it can be reduced to a standard form. This form, standard form. This is the standard form. So we will learn it. There can be several feed forward loops, different. Because what is the forward? Feed forward. Going forward. Here. Going forward. Sometimes there will be some feedback. What is that feedback? This is the feedback. So here this is this is forward loop. This is feedback. Can be in a different direction. Signal is going the direction. Signal is going in back to the direction. So forward and back feedback, different types of loops there will be. So how can you solve it? First of all, first rule. There are 8 rules. 8 rules. We will learn each rule one by one. First rule. Combining the blocks, if it is in cascade, cascade means series. So here if we have 2 signal G1 and G2, these are in series. So when blocks are in series, what happens? We will multiply. If the blocks are in series, just look at this. These two in series. Cascade. What do we do? We multiply it again. We multiply. So combining the blocks. If there are 2 blocks are in series, then we will multiply again. Here, G1 multiply G2. Second one, combining the blocks in parallel. Parallel. Here, there are 2 blocks are in parallel. This is the parallel one with the summing point. What will happen? We will add. The gain will be added. here G1 and G2 are in parallel, and the gain will be added. G1 and G2. Look at this. These two is in parallel. So what will happen? These two will be added here inside. This will be added. This is not what actually the block diagram. This is the block diagram representation. We need to reduce the block diagram. So these are actually the rules. The first two rules. First rule: if the blocks are in series, the gain will be multiplied. If the blocks in parallel, the gain will be added plus. Now, two more rules. The first rule, this is important. Moving a summing point behind the block. So, if a summing point behind means after. Behind. Moving a summing point behind means after a block. Here, I have a summing point here. This summing point I want to move after a block. So what will happen? We need to multiply with a gain G, with the same gain. How can we derive it? How can we derive it? Let's do it. Okay, here I have, I am writing 3. I will prove it here. I have a gain here. And here we have a summing point here. Positive and negative. Okay. Let's consider I have two inputs here. I have two inputs, R1, R2. Two inputs, R1 and R2. So now, this is first we need to find out the output. What will be the output? What will be output? This is R1 minus R2 here. R1 minus R2. And then it will be multiplied with again G R1 minus R2. Okay. Now, if I want to move this after this block, let's see. I will redraw this. I have a gain. Now I have a summing point here, and that summing point I have R1 here. I have R2 here. Now, first of all, we are not considering that. We are just moved that. Now, find out the gain, output. First, this is R1 multiplied with G here. R1G. Now, what about this output now? R1G minus R2. Is it same? No, it is not same, but the output must be same. When you move a summing point, the output must be same. Here it is not the same. I moved the summing point here from this, and it is not the same. So here it is R2. So what we need to do? We need to multiply with the gain. Then we can have the same. Now we have G. So we can have R1G minus R2G. So now the output are the same. So when you move a summing point forward or backward, the output must be same. That's why we need to use that. So this is the proof.